Ka tangi te titi, ka tangi te kākā, ka tangi hoki a hao te he Māori ora. E na mana e na reo au rā rakatira mā tēnā koutou, tēnā koutou, tēnā koutou katoa. Tēnā kā tūraro o te maru o ka mana whenua, ka te māmoe waitaha kaitahu, no mai haramai welcome. I stand here beneath the cloak of the people of this place, ka te māmoe waitaha kaitahu, and welcome you here. Ki te whare, tūnei, tēnā koe, tū tonu. To the house that stands here, greetings, may you stand forever. But in case of an emergency, and that may be under threat, please use the exits provided, or in an earthquake, drop, cover and hold. And mate haere hoki atu rā ki te po, and let's remember at this time those that have passed before us. Ko waiao, no otopoti hau, ko Kotharani te iwi, he kaimahi ahota o tako whakaihu aka ko Richard Blakey taka wingawa. So greetings everyone, I'm Richard Blakey, Deputy Vice-Chancellor of Research and Enterprise, University of Otago, and it's my great pleasure and privilege to be welcoming you here tonight for this inaugural professorial lecture where we celebrate the promotion to the position of Professor of Peter Whigham. The order of proceedings is quite straightforward. We are all here for the main event, but we do want to make sure we get the best out of our regalia and our celebrations by having a number of people in the academic party, tēnā koutou, having various roles. We will have an introduction by the Pro-Vice-Chancellor Division of Commerce, Professor Marie Tyne. We'll have the main event and we'll have a vote of thanks at the end before we get invited to the staff club for some refreshments. So welcome here everyone, welcome to members of the university community, welcome to special guests of our speaker, both in person and online. I think some of those special welcomes will be made next, but what my role is both to congratulate Peter on his most well-deserved promotion, but also to give you a little bit of an indication of how special this is. A promotion to the position of professor is the peak academic promotion at this and any university, and we take the process very, very seriously. We do require that the criteria are met for excellence in research, teaching and service, and that is benchmarked by the use of international referees. It's not just excellence in specific time-limited areas, but it needs to be sustained over significant periods. Marie will tell you a little bit more about Peter's career and where he has excelled, but in reviewing the CV, I could see that we have a very clear case for promotion here, that teaching has been at the highest standard, research has been highly collaborative and collegial, and service has been multifold. Peter was nominated for OUSA awards, lecturing and supervising, so both at undergraduate and graduate research levels. And there is a specific indicator that, to me, talks about how wide and extensive his collaborations are. He has collaborated in PhD supervising, I think, 29 doctoral students, with members both within and outside the university, but within the university, other collaborators have been from all four of our academic divisions. That is highly unusual. I've invented an index that I'm going to call the Whigham Index, because the number of unique supervisors for his 29 PhD students is 32. So that's a ratio of more than one. That's a 32 divided by 29 is 1.1. And so anyone with a Whigham index of more than one is a highly collaborative and sought after supervisor. So congratulations on getting the highest Whigham index of anyone in the world to date, Peter, and in particular, congratulations on behalf of the university for your most well-deserved promotion. Well done. Thank you very much.
Professor Blakey, tēnā koe. Professor Barker, tēnā koe. Associate Professor Dick, tēnā koe. And Professor Whigham, tēnā koe. Desley, Tama, Colin, Lynn, Zara, and extended whānau and friends, tēnā koutou. Friends and colleagues, tēnā koutou, tēnā koutou, tēnā koutou katoa. Ko Marie Tain Tokawingawa. I have the distinct privilege and pleasure of being the Pro Vice Chancellor of Te Kula Pakahi, which is the Division of Commerce, and that is the division which Professor Whigham, in his Department of Information Science, was housed for 22 years. And it is my absolute pleasure to warmly welcome you all here today for Professor Peter Whigham's Inaugural Professorial Lecture. Now, Peter and I were discussing this event earlier this week. Peter insisted that I did not spend long in preparing for the introduction, and in true Peter style, he said I could just make something up and probably wing it. Well, Peter, I'm not actually sure that I could make this up. Your remarkable achievements and contribution to academia, the wider community, are actual facts, which rightfully have been acknowledged by this very well-deserved promotion, and indeed it was a slam dunk. Professor Whigham received his PhD from the University of South Wales, after which he continued his work in Australia's Commonwealth Scientific and Industrial Research Organisation as an experimental scientist. His early research focused on developing innovative computational methods and models to better understand ecological systems, leading to an exploration of a fundamental question: what is the best way to describe and model spatial and temporal processes? This question has remained central to Peter's research, driving his curiosity and leading to the development of an evolutionary algorithm that explores sentence structure defined by grammar, a model now widely used in the field of genetic programming. Peter's move to New Zealand and the University of Otago in 1999 marked the beginning of a significant chapter in his academic journey. Since joining us, he has continued to push the boundaries of computational modelling, applying his expertise to a vast array of fields, including ecology, economics, public health, medicine, geography, anatomy, and structural biology. His work has transformed how we approach problems in both natural and social sciences, offering new insights and methodologies to tackle some of the most complex questions in these fields. Peter is a true multidisciplinary researcher, collaborating with experts in a wide variety of fields, from surveying and design to botany, zoology, and even adolescent sleep studies. His current work on satellite methods to detect methane emissions, for example, is a cutting-edge project with far-reaching implications for agriculture and climate science, reflecting his ability to apply computational models to real-world problems that matter on a global scale. At its core, Peter's research is about understanding complex systems, whether they be ecological, economic, or biological, and using that understanding to improve the world around us. In a time when global challenges such as climate change, public health crises, and economic instability require innovative solutions, Peter's work provides powerful examples of how computational models can be used to address these urgent issues. Peter is a prolific publisher of his research, 58 journal articles and 64 refereed conference papers, and he has been awarded significant research funding, including a $6 million MB research fund. Beyond his research, Peter has made an indelible impact as an educator. He has supervised, as we've heard, 29 PhD students, including people in this room, and continues to publish with a significant number of them. His commitment to supervision and teaching excellence is obvious, not only in the number and variety of supervisions, but also in the amount of teaching that he has been involved in. As we've heard, Peter has been recognised with numerous teaching awards, including 2 OUSA Top 10 Teaching Awards, and has been nominated for 2 OUSA Supervision Awards. Supervisor of the Year Awards, I should say. These awards are a testament to his dedication for his students, his passion for teaching, and his ability to communicate complex ideas in a way that inspires curiosity and understanding. One of the qualities that truly sets Peter apart is his ability to make research accessible and applicable. He has not only excelled in the academic circles, but has also fostered strong connections with industry. His collaborations with companies such as Silver Fern Farms and ADI Instruments have provided practical solutions to real-world challenges, demonstrating how academic research can be translated into meaningful societal impact. Whether it's optimising business processes or developing innovative tools for healthcare, Peter's work bridges the gap between theory and practice, ensuring that the benefits of his research extend well beyond the university. Peter's collaborations are not only multidisciplinary, but they also span the globe, from partnerships with the University of Illinois and the University of Arkansas, to his work with organisations such as the Environmental Defence Fund and Global Methane Hub. In addition to his academic achievements, Peter has made a significant contribution to the University of Otago through his service and leadership roles. As a key figure in the School of Computing, he is actively helping to shape its direction. Peter's cross-discipline interests are reflected also in his university service roles. Not only does he commit to service roles in his school through divisional board, teaching and learning committees, and promotions committees, but he spans the divisions and the university with his service roles. In roles on the Interdivisional Undergraduate Board of Studies, the chair of the Ecology Board of Studies, the chair of the E-Research Advisory Group, working party member on environmental studies, University Research Committee, the UORG panel member, and a Senate member. Having had the privilege to work with Peter, especially for the last 2 years on our Commerce Divisional Board, I can honestly say that this is a colleague whom is always ready with a wise word, a statement, or a piece of advice, and who certainly keeps me on my toes in any committee meeting. Peter's knowledge of various disciplines is vast, and I am always grateful to be able to tap into it. As we have heard, a promotion to full professor at the University of Otago is not a step taken lightly. You must excel in all 3 areas of the role: teaching, research, and service. Peter Whigham has gone above and beyond in all 3, and his work continues to inspire students, colleagues, and collaborators alike. Like many others, I feel privileged to work alongside Professor Whigham, and I am delighted to be able to warmly welcome him up right now for his inaugural professorial lecture. Please welcome Professor Peter Whigham.
Kei mi kia korua, mō te whakatimatanga o tēnei pokinga. Kei mi kia koutou, mō te harimai, Māori ora, and welcome. The language of models, I should start by saying, for the people online, kia ora to those in New Zealand, kia ora South America, kia ora Canada, kia ora Europe, g'day Australia. The language of models. Models broadly can be 2 types. You can build a scale model and then test that in such things as the physical environment, or you can build theoretical models, computational models. I am definitely in the world of computational models, and here's why. The Stirling engine. So are there any questions? And don't be fooled, I didn't build the Stirling engine myself. So I'm clearly someone who works in computational methods. They might be mathematical, they might be simulation models. We've done quite a lot of work in these areas. So this is a simulation model of speciation over a food web and structured in space. But the main area I work in is in using data and understanding the properties of data. And this is the kind of flow chart of my world. So here's the real world, or there's some process in the real world that I'm interested in understanding. And it's interesting to remember that you start by sampling this world. This is a complex world that needs to be sampled. And there are assumptions in the way you sample. And there's simplifications, of course, because you cannot represent all of the complexity that's here. But you ultimately end up with a set of data. And from that, you build a model of some sort. And that model could be just about the properties of the data. It could be because you're going to build a simulation, or perhaps you're going to use it for prediction. But either way, the most important aspects of any model is that you want to be able to explain and understand, confirm hypotheses, test new ideas related back to that initial process that you were sampling. And this is really the world that I like to live in. And you might think, well, that's going to mean complicated models are the only way we learn interesting things. And that's just not true. Here is perhaps the most famous straight line ever drawn. Okay, in 1929, Edwin Hubble had collected enough data on the distance to stellar objects through luminosity and the velocity of stellar objects through redshift, think of it as Doppler shift for light, and from that he could draw a straight line. It was velocity given some slope times distance, and so beta 1 is the gradiental slope of this line. A single straight line allowed him to infer that perhaps the universe was expanding. Remember, that took another 40 years before that was settled. But more importantly, he could calculate the age of the universe. And with the data he had, he came up with about 12.6 or 12.8 billion years, which is just extraordinary from the time it was made and the quality of the data. The thing to remember is it was a straight line. So you do not need complex models to make important decisions and important knowledge. Very brief bit of history. So I did my undergraduate Bachelor of Honours degree and finished in 1983 at the Australian National University. After that, I worked as a tutor. I had a business with two colleagues, John Bishop and Norval Hope. They were fantastic people. John taught me how to program. We would have been a great business, but we could not manage ourselves. And eventually, this is serious, unfortunately, and then eventually I joined CSIRO. I was in the same division for the entire career of 12 years or so. What's interesting is that it started, or here are the three names. At some point we were the Division of Water Resources, then we were the Division of Water and Land, and then as a final twist that no one saw coming, we were the Division of Land and Water. It was an interesting place to work, I can tell you. But during that time, I published a paper in 1990. We were working on expert systems. These are very simple ideas, popular in the 80s. If I don't have a great deal of data and I want to model a system, well, I'll go and talk to an expert. Hello, Richard. And he will tell me some information and I can write out, say, a set of rules that describe the process he's interested in. And I can then put that in a computer and I can model it, I can do simulations, I can do predictions. We were interested in largely ecological systems and certainly geographic systems. We were interested in how space worked. And so we developed a spatial expert system. And you can see here's a grammar that describes the language of space. And this allowed us to write rules that talked about how the world interacted in a spatial sense, and how elements in space could talk to each other and how that influenced those processes. And it was quite a successful, successful model. My favourite application was that we worked with the army at Puckapunyal at the training range, and we modelled armoured vehicle movement for training, which included Unimogs and APCs and Leopard tanks. To get those rules, though, I was the expert. So I had to read the Tank Troop Driver's Handbook. I had to go out on live firing events and watch, and spent overnight in an APC with live firing that was completely horrifying. And I wrote the rules in the end to describe how armoured vehicles moved around a landscape, how they damaged the world, and how much it would cost to repair that damage. So it was a really successful project, and it was interesting because it involved language and spatial processes. At some point during that, my wife, or soon-to-be wife, Desley, said, "You should really get a PhD because otherwise you'll regret it." And which in other words is, I don't want to live with someone who's constantly annoyed for their rest of their lives. And so at the beginning of 1993, I started a PhD at the University of New South Wales. These are notes from my first year of doing my PhD. And I was interested in, the spatial expert system was a great idea, but you had to have an expert to write the rules. And I wanted to take data and then some very flexible form of model and learn that model structure from the data. Right? It seems like a sensible thing to do. And so this was my machinations. I was very good at playing pool by the end of my first year of a PhD, and I'd made no progress at all. So what do you do at the end of the first year? Well, you go and get married, because that would make sense. So after the first year of a failed PhD, we got married. And what do you do on a honeymoon? You go to bookshops. And Desley pointed out this book on complexity and said, "Oh, this might be something you'd be interested in reading." And she was right. And in particular, apart from it covering interesting things about processes and complex systems, it also introduced me to genetic algorithms. And I thought, wow, they seem really interesting. And just to give you an idea of why I thought they were interesting, they're very good models to search complex spaces. So imagine, well, here is think of it as a fitness landscape, and if I look at it from above, we're trying to find that spot in the middle that is the lowest point of this landscape here. Now, of course, you can't hill climb this, and yet a genetic algorithm can find the solution. We'll just watch it run. How does this thing work? It's a population of individuals. They breed together, and we have sort of Darwinian and Wallace natural selection. Notice I threw in Wallace. To do selection on individuals, and they mix their genes together, they mutate themselves, and eventually, if you're very lucky, they find some interesting properties that solve the problem. So it was a really interesting fundamental concept. So the honeymoon finished, and I went back to starting the second year of my PhD, walked into the room where I was sharing a room with Paul Darwin and said, "Paul, I like genetic algorithms, but they're all fixed length structures, and I want a variable length structure." And he said, "Oh, go and have a look at genetic programming." And fortunately, remember, there's no internet here. We can't do a Google search. But fortunately, John Kozer's original book was in the library. So I spent a couple of months and I built a genetic programming system and then wrote up a technical report describing my conclusions. It seemed like a pretty good idea. You could build variable length structures, it could build variable length programs, but it was completely unstructured. There was no way of adding domain knowledge. There was no way of talking or constraining the way in which things were expressed. And certainly you couldn't talk about first order languages or any properties like this. So it seemed like a good idea at the time, but it had some problems. But I knew about grammars. So you'll recognise the name Noam Chomsky probably through mainly his work in public, well, not public health, in the whole issues of disputes around things and public good and so on. Noam Chomsky was a brilliant academic, and in the 50s and the 60s he redefined the notion of language and came up with such things as universal languages and universal grammars. And he understood how important a language was defined by a grammar. And in particular, we can see on this page, and I'd read this paper many years before, any language you can think of is an infinite set of possible sentences, which is true. You can say an infinite number of things in a language. But a grammar is a finite device that encapsulates that infinite set of sentences. And in particular, a grammar is a sentence, that grammars can be viewed as sentence generating systems. And I knew this, right? And just to give you a brief idea, here's a grammar, a really simple one, just because I need to use a bit of terminology. These, on the left-hand side, these are called non-terminals. So these are going to be rewritten to give me the thing on the right-hand side. And on the right-hand side here, we've got what's called a derivation tree. So we start with, say, a statement, and then we're going to apply this derivation. So we get that section there. And then, of course, all the non-terminals eventually have to be filled in to the point where at the end, we've got that final set of terminal symbols, and that's a sentence in this language defined by this grammar. Okay, so you've got this notion of a grammar. We've got this notion of a derivation tree, which talks about the non-terminals and how they're expanded. And we have a grammar that defines this infinite language. And we knew all of this. And it was only that, so there was a visitor from AT&T in the States, William Cohen, soon after I'd looked at genetic programming. And we went out for a coffee with my supervisor, Professor Bob Mackay, and we were talking about grammars, and William said one sentence that made my PhD, because he said, you realise if you take two derivation trees, and pick up the subtrees at the same non-terminal and swap them, it must still be in the same language. And we all went, oh, yeah, of course, it has to be. And so that was the end of it. So that solved the problem of what we needed to do. So here's an example from a review paper in 2010 that I was a co-author on. So here's the idea. These are two individuals, and these are the derivation trees. If I pick up this derivation at the point NP, and here's the other one with NP, I can swap them over. So we've got the cat sat under a mat and the big red dog stood on the floor, and I can swap them over to create the floor sat under a mat and the big red dog stood on the cat. And they're both now still sentences generated from the grammar. It was such an obvious link that we just couldn't see. And in the same way, so this is now like the way you take two complex individuals and mix them together. In the same way, we can mutate individuals. I can pick a non-terminal like NP and throw away the tree and then just get the grammar to regenerate a sentence starting at that non-terminal. So we go from the big red dog stood on the cat to the cat stood on the cat. We don't care what it means. But suddenly that was it. I needed ways of mixing together expressions. I needed ways of mutating so I could generate new diversity. And the problem was solved. So after that conversation, I spent a couple of months and I wrote my own context-free grammar system in genetic programming. And by November of that second year, I'd written up the technical report describing the properties of this language and this model. And it worked really well. So for example, here's a grammar that talks about, we're trying to model greater glider density. It's a marsupial in Australia. And I wanted to produce a set of rules to do that inference. And so here's a grammar that generates if-then-else style rules and captures spatial relationships. And we could search the language expressed by that grammar to find ways to understand about the density of these marsupials. And so things like this result here was better than all the other models in terms of data it had never seen in doing predictions. We clearly had a model that allowed us to express language bias, have search bias, domain knowledge, and search for complex models. So I thought that was great. Just as a warning, so of course, because it was a grammar, I could also do mathematics. Here's a tip for those who are still doing a PhD. Don't involve your wife, spouse, or any other partner. Desley kindly offered to read a draft of my PhD. She found a mistake, and I'll call it a typo, on some part of my mathematics. Right, so now she goes around saying, one, oh, I gave you the original idea because she gave me a book. And two, I fixed the mathematics in your thesis. So anyway, I went back to CSIRO, we started doing other stuff. It was mainly in ecology. Occasionally I'd use this model that I'd built, but it was kind of, I felt like I'd solved the problem and we had other things that were interesting to do. I occasionally did things. I wanted to work with Dr. Peter Crapper, because I definitely wanted to have a publication with that name. And we worked on, and it's fantastic, he was a great friend. So we did things like rainfall runoff modelling. I worked a lot with Friedrich Recknagel from the University of Adelaide, mainly on freshwater systems, using the model. But largely didn't really push the model and was doing other things. And this slide is because I have to acknowledge Grant Dick, and I'll come over and shake his hand, because Grant was a PhD student of mine and we did some stuff on evolutionary algorithms, but post that PhD, I didn't really push anything about my model, my context-free grammar genetic programming system. And Grant took it on himself, thank you, Australian accent. Grant took it on himself to push this method, and we published a few things together, and he wrote reference systems so people could use the code and so on. And he really pushed and promoted the method. And because of that, so here's an example from 2017, people write things like, Whigham pioneered the use of grammars in GP, while grammatical evolution mainstreamed the use of grammar-based approaches to the point where it became one of the most popular methods in genetic programming. That's Grant. Without that, I would have been lost in the history of things. So I really do appreciate that. What's interesting, so this paper from 2017, you notice the conclusion at the end. The results show that in most of the selected benchmarks, we do about as well as my version, which really means, and we did worse in some. And they're comparing it to a model that's nearly 25 years old. Right? We had one other, and I have to indirectly thank some Irish people, Professor Michael O'Neill and Conor Ryan in particular, from University of Ireland, University of Dublin. They really pushed this approach, and it was because, and euro dollars were pouring into Ireland around the late 90s, early 2000s. And so they really are the ones who promoted the method. But unfortunately, they don't like Grant and I very much. We were invited to write a commentary paper from Lee Spector, who was the editor of Genetic Programming and Evolvable Machines. And he said, write a philosophical work. So we said, okay. So we got James Maclaurin, who's a great philosopher of science and also a philosopher in terms of biology and evolutionary systems. And so the three of us wrote an article about evolutionary algorithms and how they should work and what would be the best style. And in a fairly brave move by Lee Spector, he said, okay, we'll do it as a special issue, and then I'll invite a whole bunch of people to write commentaries about your inflammatory piece of work. and you can then get one rebuttal at the end. It was a tremendous piece of work. Unfortunately, it means there's a lot of people in Ireland and Spain that don't like us. Okay, let's change pace for a while and talk about cats. So everyone's waiting for the cats. So I have a cat called Olive, and we had a problem with Olive. Well, we didn't have a problem with Olive, but there were other cats that seemed to be coming in and eating her food. And that seemed to be a bit of a problem. So I thought I can solve this computationally. And so just to give you an idea, let me just start this up. So the very first thing, of course, was I just had to understand what was going on in the laundry, right? Because the laundry was where her food was. And in case you've never written software to do things like detect motion, clearly it feels like you just take two frames and add them together and find the difference. It's not quite that simple. So for example, you start by smoothing out the world. You can see me smoothing the world out here. You turn the world into a set of blobs. So if I stand nice and still, it'll all disappear, and then up comes the hand. And of course, in the end, after all of that, you can start to track the object. And then of course, I want to take pictures of just the bit of the scene that's actually moving around. So we first of all just wrote this software so that I could find out exactly what was going on. This was kind of strike one in our family, because I had to make lots and lots of pictures. In fact, we ran this system, and of course, and there are members in this room who were part of this picture. People would drop by and they'd say, oh, I'm running an experiment in the laundry, and they'd all go and have a look. But this is not Olive, this is the other cat. And just to point out one thing, this is the laundry door, and you'll notice it's brown. Just remember that because it's important later on. So we took thousands of, they were probably the most photographed cats in New Zealand for about a month, right? There were thousands of photos. Strike one was that I wasn't allowed to look at them till after 10 o'clock at night because it was so fascinating I just couldn't stop looking at them. But eventually I'd built up a large repertoire of them, and because of that it was reasonably easy for me to build another model that recognised whether Olive was in the laundry or the other cat. And it was only one cat that was eating all the food. And that cat had a really strange behaviour. So step two was that I just wanted to look at their behaviour. So yeah, this is almost strike two. So you can see Olive would turn up in the morning and maybe have some morning tea and a bit of afternoon tea and then pop in for dinner. And the intruder would almost mimic those timings. If we look at another day, it looks suspiciously like the intruder cat was watching Olive. She'd go into the laundry, come back out the cat door, and the intruder would wander in and help herself. And she was a ferocious eater. So step three was that I started taking videos to see what the behaviour looked like. But this cat was a machine, right? Okay. Now, of course, once I knew that, we got to the next stage. Oops, which I want to just go back. Right, I'll just make sure I don't miss it. So now I could identify the cats. Now we get to the treatment. And we decided that the best noise, so I set up some speakers, and the best noise we decided on was a really harsh harmonica noise, because that seemed appropriate. And so this is the sort of thing that happened. Let's just get to here. And it worked really well. And by the way, I turn off the harmonica noise after about 2 seconds on for this video because it's so damn annoying. So that worked well, but the cat genuinely got more and more interested. Right, that's the original behaviour. Let's look at the next behaviour. But watch what it does now. Right, and I've turned off the sound, but you can see the ears. It's still playing, right? The harmonica's still going. It was desperate, even though it didn't look thin, it was desperate to end. Look at this. That's right, we're watching you. And so you think, if I anthropomorphise the cat, it was watching Olive go into a room and nothing would happen, then it would go in and it would get, all hell would break loose. And eventually, what are you going to do if you're the smart cat? Well, you'll come in with her because clearly there's no problems. So, of course, that's what happened. And the harmonica goes off because it didn't care about Olive so much, and it ran out. And Olive eventually, she must be tone deaf, she eventually left. And because it was turned up quite loud, we'd be at the other end of the house and we'd rush down to see what happened. The interesting thing, that was the last time we ever saw the cat, right? And it had gone through that long process of working out what behaviour was trying to do, and it realised there was just no point. And so we'd solved the problem. We've got a dog, We've got a dog called Charlie. And I thought, well, gee, I'm on a roll here. So I checked with Charlie and said, have you got any problems I could solve? And he said, no, he's fine. So I just carried on with other things. So here's a more serious example. Simple model, but one that allowed a lot of insight. Really nice work. Kath, how are you? So I did a lot of work with Professor Kath Dickinson. This is a PhD student of ours who's now Dr. Harris. So Kim was interested in looking at the Otago grand skink, and she had 4 regions in Macraes. And the grand skink live on rock tors, and then they move through the matrix, be it the surface area, be it a pasture or a grassland or some sort of ploughed region, and we were interested in their behaviour. And so here are the 4 sites, and we turned the rock tors into networks, because the insight was, well, realistically, the way they move around in this network is related to the rock tors and their positions, and you're going to find that if you have a more rich and dynamic way of moving around in different environments, that may be an influence on things like the density of the ground skink and the health and vitality and so on. No one knew what the home range was, so we just gradually looked at extended distances, but we knew it wasn't 14 kilometres. But what this allowed us to do was characterise the landscape environment in a way that wasn't possible without changing the way we thought about the world, which was a simple idea, but it allowed us then to measure properties of these networks and link those back to things like the number of the way rock tors were used and where they were living and so on. So a really interesting, simple piece of work. Some work with Matt Parry and Grant Dick. Hi, Matt. We were interested in morphing networks because it seemed like a good idea at the time. And so here's the idea. We start with a regular network and we just gradually want to change it, just flip edges and move them around, but not to just make a random network, which is here, but to go all the way through a vast class of different types of networks. Now, why am I interested in this? Well, you think what we'd like to do is say, here's a regular world, and then there's a vast array of different ways the world could be connected. And so we designed an algorithm to go from a regular world through sort of small world, scale free, and all the way to something that looked more like a star. And okay, there are worlds that we wouldn't have touched on, but it meant we created a vast array of different topological structures. And what do you do with that? Well, you run models over the top of it. And what was really attractive is that the x-axis here is basically all the ways in which the world changes. So here was a simple epidemiology model, and this was a measure of the selection strength required to achieve half of the population being taken over by a virus or a mutation. And the unfortunate results were that, of course, it's much, much easier to propagate viruses down here, and no surprises, this is kind of the world we live in now. So I think everyone knows this, but the way in which our world is structured promotes the propagation and the propagation of viruses. Here's another sad story. Well, a sad story in a strange way. Caitlin Owen, I think Caitlin's here maybe. Oh, hey Caitlin, sorry. Yeah, Caitlin at the time, Dr. Owen was a summer student, and I'd come up with an idea, and after 3 weeks she said, this doesn't work. And I went, okay, well, let's talk to Steve McDonnell. So the professor was just down the corridor, and he said, have a look at software effort estimation. It's an interesting field that I've worked in. And we went, okay, well, let's have a look at it. And here's a tip. You know when a field is having problems when most of the publications are things like, my model is better than all these other models and everything else that's ever come. Right? And then the next paper will be, my model's better than linear models, decision trees, random forests, and your mother. Right? And it will just go on and on. This is the quality, this is a good indication of disciplines that are failing. And so we thought, well, look, what they need is at least a good baseline model. That would make sense. If they've got a base that they can say, well, I'm better than the baseline, at least you've got to start. And strangely enough, there was no decent definition of a baseline model that we could find, so we had to write our own. But no surprises. Think of it, a baseline model's got to be simple. It's got to be deterministic. Right? We want to run it and we get the same result if we give it the same data twice. It's got to use qualitative and quantitative data. It's got to use numbers, it's got to use categories. It would be nice if it could give some explanatory information about its behaviour. And critically, it can have no parameters that are tunable. Right? You can't have a model that's tunable and be a baseline model. So we defined this, and our baseline model was just a simple linear model, but a linear model with a slight twist. So here's some example data that's used in software effort estimation. And a lot of that data was highly skewed. And I was originally very suspicious that when they said my model was better than a linear model, it's because they didn't know how to use linear models, right? And so the method we did was to say, well, look, I could automatically transform variables by looking at their skewness, looking at their shape, trying a few functions on them, a log and a square root and a square, measure their skewness again, and if it sort of fixes it up a little bit, I like things that look kind of like a hump shape, well, I'll keep that. And I know how to turn the data back at the end, so I can build the model and run it and then turn everything back. So for example, this is the distribution. If we watch these last two here, that's their distribution when we apply a log function. So we've gone from data like that to data that is much, much friendlier typically for a linear model, even though there's not a great deal of theory that says it should be. So that was our baseline model, no parameters, no tuning. And here's the bad news. So the baseline model was now outperforming just about everyone. So for example, here was a 40-page model on using an ensemble of artificial neural networks, and the baseline model beat it on the 3 data sets that we had that we could compare. Right, this is the baseline model that we're trying to propose. Once again, it showed the field really needed a little bit of support. A really simple model. This is why the world, academia is a strange world. So we published that, and very soon afterwards, I got a phone call from New York. So Gregory Goth from Communications at the ACM calls up and interviews me for an hour from New York because of the baseline model, right? It made no sense to me. Anyway, so he published that in the magazine after the interview, and we all walked away saying, I don't get it, and I never published in that field again. Strangely enough, a few years later, someone did this publication. Another baseline model, right? I thought you only needed one. But anyway, it's a strange world. Here's a much more interesting problem. This is work with Professor Paul Glue from Psychiatric Medicine and Brendan de Graaf from Public Health. So we were interested in social contagion. And what do we mean by social contagion? Well, even back to Plato's time, you know, they knew friends all looked similarly, or you could say birds of a feather flock together. So social contagion is about the fact that you might see things grouped together in space, probably because they have similar ideas and so on. So the data we had was on deliberate self-harm from Invercargill for 2 years as admission to the emergency department, and we knew where the people lived. That was the only data we had. And of course, they were distributed in space. So let me just explain, before we go to the complications of it, here's how, if I just had a set of a space with some points, and we had point data, how do I determine whether it's clustered or dispersed? So here are a set of points that are clearly clustered. Ripley's K is the standard method for doing this, and all of this is just saying, measure, stand at a point, and gradually increase distance and count how many points you see. And you can imagine if it's really clustered, you'll see lots of points early on. And that's this black line here. So early on, small distances, we see lots and lots of points. This grey envelope here is if we take all of those points and just randomly throw them on the space and then measure Ripley's K and do that many, many times, it's like an envelope a confidence envelope about the behaviour if there was just a random world that we were sampling. So Ripley's K is quite interesting. And then these are dispersed points, so no surprises. We are below the envelope to start with, and eventually distances get larger. So okay, so we can measure clustering. It's not going to solve our problem because the world is not random. So we had at least 2 things that were interesting. One was that the people themselves that we were measuring and asking about social contagion weren't distributed through space in any sense evenly. This is their distribution using the deprivation index. Thank you, Peter Crampton, for developing such a wonderful measure. And this measures effectively like economic quality. So 10 is quite poor and 1 is Murray Hill. And you can see immediately the people that we were trying to study didn't live in that. So if we were going to generate random examples of where they could have gone, we had to control for deprivation. So our randomisation had to basically follow this distribution. So at least then we'd feel like we've controlled for deprivation. Secondly, in Invercargill, you can't just live anywhere, you have to live in a house. So you can't live in spaces that are empty and so on and so on. So we had to get the map of all the properties within Invercargill, be very careful about where they were houses and not warehouses and so on. And then we had at least places we could put people so long as we ensured that the deprivation distribution. Invercargill also looks suspiciously like a grid. And I was very fortunate to give a talk on this work before we'd published it, and thank you, David Ayres, for pointing out, because he said, well, look, if it's on a grid, and I'd said to him, well, we're going to use an L1 measure, which is a Manhattan distance. So you think it's like, you know, from this point here, I can walk along that street and then up, and it feels like I can only go in the grids. And that's the way, and so this is called an L1 Manhattan distance. And I was going to use that to measure social distance. And Peter was kindly pointed out by David that you should get rid of the bias in the fact that Invercargill is a certain shape and rotate the Manhattan distance and run the models for the rotations. Because we were trying to get rid of any effect and hopefully showing there was no social contagion. So thank you, David, because it was a significant improvement in what we were doing. The unfortunate results were that we could not get rid of social contagion. So up to around 500 metres, it appeared there was some strange social contagion going on. There is no explanation for this, and it could literally be, this is why working in these areas are painful, it could be that maybe the distance to a dairy, right, is the co-founder that actually would get rid of all of these effects. Right, maybe it's the distance to a pub, maybe it's some other, you know, the closest distance to a park. It could be some spatial relationship that would remove this effect, but we can't measure everything. So extremely difficult to actually confirm it, we just couldn't get rid of it. A couple more examples I'd just like to briefly talk about. So great privilege to work with Professor Kim Meredith-Jones from the medical school, and we're looking at sleep data. We've got about 130 adolescents, and they've been measured with a polysonograph overnight, plus there's a whole vast array of data about them behaving for several days. There's video data, there's acceleration data for days and days. So I'll just explain what this is. So this is called a hypnogram, and this is determined by using a polysonograph, which is like an ECG, an EEG, measuring temperature and heart rate. And in fact, there's about 5 or 6, 7 measures. And then you have experts that have a vast manual that explain how to code states. And each of these states here, each of these lines here, is 1 30-second coding of behaviour. And so they take this vast array of data and say, over this 30-second period, you were in the N2 sleep state. And they do that for every 30-second period over an entire night's sleep. So you can see here they were awake at the end. And I've shown you this one because it's a pretty classic, this is one of the adolescents, but they really do sleep like the textbook says. You typically fall into a deep sleep early on. This is why if you get woken up after about an hour or half an hour of sleep, you'll be very groggy because you've gone down to N3. And then they'll pop up maybe to a slightly lighter sleep. Here's their first period of REM sleep, and it's shorter. Then you have another period of REM sleep after some other deep sleep. And then the third period of REM sleep's the longest. And this is the classic theory of how people sleep. So this person was great, but you can see lots of noise here, right? It's not a case that from the measurements they've got that you are definitely asleep or you're definitely not. So from REM especially, you often get periods where they say you're awake. Now it may be physically you can't notice anything, but internally your brain is now in a state that they've characterised as being awake. So it's fascinating data. So for this data, we can do things like build graphs that describe the state transitions of hypnograms. And if we've got graphs like this that are state transitions, we can go and look at Markov models. We can look at hazard models because we've got data associated with every individual. I've done a little bit of work with this, but haven't got a lot of traction with it. In fact, what I'm really interested in doing, a bit like the let's do a baseline model, I'd like to build a model that was what's normal and abnormal. Because I was going to show, but decided against it. Every hypnogram is different. And yet the adolescents that were being measured had been screened to be all people who did not have sleep problems. So that whole question of how do you measure normal in its pattern of sleep is a really interesting one, I think. So we can take this sort of data and build features from it, but what's also more fun is that, of course, we've got things like acceleration. They wear a bunch of devices like accelerometers. Think of a Fitbit, but one that works. And so we can measure things like acceleration in 3 dimensions. We can measure temperature and heart rate and so on. And for our period of sleep where they were being measured, they were labelled data. So we can build a model, certainly of awake and sleep. And we can do that in 2 ways. One is to construct a set of features from the data, from the 30-second data. So we build models that look a bit like this. Or we can take the raw data and jam it into some sort of neural network, which I continue to try to get to be better than the features, and I can't. But it's a work in progress. But it's a fascinating area because the data is very rich, it's very complex, individuals are all very different, and there's lots of interesting questions about that. So I'll finish up by the final model. Very fortunate to have a wonderful PhD student, Christian DeFago, and Christian's from Columbia, and we're modelling the source of methane. And there are satellites now, like Sentinel-5, that and using tropamine, that can detect, and there's a new satellite that's just gone up, MethaneSat, and they can detect methane in a column. And you'd say, well, problem solved. Well, we're interested in agricultural methane, and so it's diffuse. So for a start, it's not like if you've got a gas leak with methane, it's easy to find where the source came from. You can see the plume and you can go back and say it's got to be here. We're interested in agricultural methane, and the big problem is that wind pushes methane around everywhere. So what we really want to do is understand, given a satellite measurement of methane, where did the methane come from and how much was it generating beyond background levels? That's quite difficult. And what do they do these days? What they do right now is you define a set of priors. This is like original guesses. This is like a bottom-up model where they say there's 1,000 cows living in this area, and my God, they're burpy. We'll give that region some number of amount of methane per hour or per year or whatever it might be. And we end up with a set of prior emissions. And this is called an inverse model. We then take the wind fields and we then try and simulate based on our prior emissions. So this is our guess of where things came from, and then we let the wind push them around. And we end up with some simulated predictions of methane, right? Remember, we started with kind of an informed guess, and NIWA provides us with some very good priors, well, pretty good priors. We've then got satellite data that says where it saw the methane, and we can use that as a feedback model to work out where maybe it should have come from. And so from that we can then calculate new guesses as to where the emissions are actually being derived from, and of course feed that back into the model and start again. This is a highly computationally expensive method, and it's fraught, of course, with a whole lot of errors in terms of there's lots of uncertainty and noise and so on. But this is the standard way right now that when New Zealand quotes their yearly budget for methane to the Global Climate Change Commission, this is where they've got the number from, right? What our intention is, of course, we need this data because we haven't got measures of methane throughout New Zealand from where they came from. So unfortunately, we had to build these models, or Christian had to build these models and run them on the Otago cluster. to be able to generate the data we could use to train the models in the first place. And our intention is that we are running models both at 100 kilometres over the entire world and at 25 kilometres within New Zealand, building a large database that actually supposedly models where methane comes from and then what it looks like. And from that, building a large neural network to be able to predict it. Now, the real value here is that, and we've got some evidence the neural network will work for this, the value will be in the future, the neural network takes 0 time to run. And so we can run our model every day, and certainly it needs aggregations in space and time, but it does mean we could give possibly, because we're using just the satellite and the wind data, we can probably give more accurate estimates of methane, say over a global year. And let's say I'm a farmer and I'm running a new pasture, and supposedly it's going to reduce methane. Over about a 3-month period, based on our mathematical models, we may be able to detect a change in methane because of that. And right now you can't do any of these things accurately. So it's a really exciting time, and hopefully that will work. I just want to finish, because I've mentioned a few PhD students, but this is a really touching book. Lisa Danusa, Kath and I supervised her for a master's, and she made this book for me. So she made and bound this small book, and she put some shrubbery in it. That's just one of them that was inside. And it was really touching. So, you know, thank you for believing in me as a student and as a person. Thank you for sharing your knowledge. Thank you for always being ready to help. And a student is shaped by the support they receive. I thought it was just such a really beautiful, touching thing, because I think it's important to remember the most important aspect is, you know, it is people, it is people, it is people. Thank you very much. I told you to bring it. Thanks. And they're a little over, but you went a bit late.
Tēnā koutou katoa, ko Grant Dick tōku ingoa. Welcome everybody. Professors, tēnā koutou. Professor Whigham, g'day. Good evening everyone. Thank you very much for coming and celebrating this with Peter tonight. I'm Grant Dick, I'm the Head of School of Computing here at the University of Otago. And it is my role, or rather my privilege, to be here tonight to give a little context on Peter's career at Otago. And I must say I do that actually with, as you can probably tell from the slides, with a bit of significant personal delight in seeing this today. So I'm quite chuffed, to be honest. So as has been mentioned, in 1999 Peter joined the then Department of Information Science, notionally to teach and to conduct research in the area of spatial information systems. However, it was very quickly recognised, again as you can see by what was in the slides tonight, that Peter was a bit of a generalist. And so he was soon teaching across many areas, including machine learning and AI, information systems, ecology, and so on. Since that time, he has supervised, I've got 28 here, I've missed one, maybe that was me, 28 PhD students, and has been alluded to many times already. Most of the supervision has fallen outside Peter's host department or school. But what's also interesting is that when the supervision was within information science at the time, almost every single supervision had some form of co-supervision with academics from within another department or another host institution. Again, through his supervision, Peter is leading by example to show how basic computational methods can inform, and more importantly, be informed by other disciplines. We could all definitely learn a lot from Peter's model of supervision. And I certainly did, as I'll get to in a minute. I'll move to Peter's service just very briefly. Peter's service covers all the bases, as has been seen here, although that's actually a bit dismissive of how he's actually led his service role. Roles such as chairing the Board of Ecology, directing the Masters of Business Data Science program, participating on the Interdivisional Board of Studies, all show an interest in reaching far beyond the domain of the School of Computing, and again, aligning with interdisciplinary roles. And then much like his teaching and service, Professor Whigham's research is wide and varied. There really does seem to be a theme in all of this, that it is wide and varied. We've heard about the achievements in grammar-based evolutionary computation. I'm sorry that you're no longer welcome in Ireland. But you have really, with your grammar-based evolutionary computation, created a field that has really taken on a life of its own in the field of evolutionary computation. As Peter mentioned, he developed the method essentially 30 years ago, and to this day it remains state-of-the-art in many, if not most, cases of its use, allowing a demonstration of Peter's insight and genius into the effective design of representation and search. Moving beyond that lasting impact in evolutionary computation, in the last 5 years alone, as you've seen on here, it's almost like I should have seen your slides, but you kept them from me as a surprise. A very effective surprise. Peter has published in the following areas: evolutionary computation, machine learning, explainable AI, software effort estimation, spatial analysis, network analysis, population genetics, financial modelling, and for some unknown reason, I'm not entirely quite sure about this, interdisciplinary research. All I can say is that that's quite an enviable and diverse array of research topics to be studying with. His current research, as you just saw again, is no less varied, including ongoing projects in sleep analysis, meat markets, which you didn't really allude to very much today, methane emissions analysis. A true generalist, Peter leads the way in demonstrating how intelligent, well-considered, simple applications of traditional computational, statistical, and machine learning methods continue to have significant impact in a range of broad disciplines. Again, we could learn a lot from his approach. I must be honest, I am left wondering what could have been achieved if we could have channeled Peter's skills and knowledge into just one single domain. I settled on tonight that something along the lines of fully sentient and weaponized cat doors that sing Monty Python songs would be my guess. So while we've been robbed of that dream, we should instead think of the numerous disciplines that Peter has participated in and the meaningful impact that he has made in those places. Now, as a final note, I would like to acknowledge the impact that Peter has had on my life personally. Peter was, as mentioned, my honours dissertation supervisor. That led to him being my PhD supervisor. He's never openly regretted that, but I certainly did make it difficult for him. And has been my chief research collaborator and conspirator ever since, including many corridor and office rants and raves about how to fix the world. Peter, you have collaborated with me on, without doubt, the most interesting parts of my research career, and you have been an outstanding colleague and friend throughout this whole time. You have been there literally at every major event of my adult life. You've been there when I started work. You've been there when I finished my PhD. You've been there when I was in Spain and I got yelled by those academics. You were at my wedding in London. In fact, the only thing you haven't actually been in my adult life is the birth of my daughter, which, let's be honest, would have probably been a bridge too far. I did try. I owe a huge debt to you. Thank you very much. Kia ora. So it's now my task to invite you all to the staff club to join us with a bit of refreshments and light banter. But before I do, I get to present Peter with the gift. So, could you please all join me in congratulating Professor Peter Whigham.